Hi everyone, I'm Ivan. Along with me, I have Sharon, Henry, and Mark. We are presenting to you the AI-driven flood prediction and urban drainage monitoring system, where every second counts. So without further ado, let's get started. This is our table of contents, showing the topics we'll be covering today. Our theme overview is as follows. So what's the issue at hand? As you can see, flooding remains one of the major environmental issues in Malaysia due to two key contributing factors, high rainfall and large river systems. When these two conditions combine, urban flooding becomes increasingly difficult to manage, especially in low-lying urban areas. The impact is not only environmental, but also economic and operational. In 2024 alone, flood damages in Malaysia reached approximately 933.4 million, while significant spending is still allocated toward manual flood management systems. Our project topic is as follows. For this project, we use the following methodology, which is from the literature review stage until the integration testing, as well as for the tools and framework we will use in this project is Mallet Simulink, React Framework, and most importantly is the Python. So when water becomes a threat, urban cities currently face several challenges during flood events. First is fluvial flooding. This is one of the two types of flooding, and it occurs when heavy rainfall overwhelms urban drainage systems. Next is fluvial flooding, which happens when major river systems exceed the capacity and overflow into surrounding urban areas. In addition, existing mitigation infrastructure still relies heavily on fixed manual operation schedules, making responses slower and less adaptive during rapidly changing weather conditions. And most importantly, the current flood management approaches still depend heavily on reactive responses instead of predictive planning. In many cases, action is only taken after flood conditions have already worsened, leaving less time for preparation and increasing the overall severity of flood impacts. Therefore, our project aims to shift flood management from reactive operation toward proactive and intelligent mitigation. So the first objective is predictive detection, using AI-based flood prediction models combined with live environmental monitoring. The second objective is automated infrastructure response, where pumps and sluice gates can be triggered automatically based on detected flood conditions. The third objective is community protection, through early mitigation and flood type classification to reduce flood severity before critical escalation occurs. And lastly, the project also focuses on scalability and continuous improvement through real-time monitoring and future AI retraining capability. With that, I will now pass the presentation to Sharon to explain the system architecture and overall project blueprint.
My name is Sharon, and I will be taking you through the technical architecture, or better, the blueprint of our AI-driven flood prediction and urban drainage monitoring system. To give you a high-level understanding of how our solution operates, we built this system with 5 main features in mind. First, we have real-time environmental monitoring, which continuously displays live rainfall, river levels, and soil moisture. Second is the rule-based flood type classification, identifying whether the system is facing pluvial, fluvial, or combined flooding. Third is our AI-based flood prediction, which predicts flood events using historical training data. Fourth is the automated infrastructure control, which translates our data into physical action by automatically controlling water pumps and sluice gates. And finally, the interactive monitoring dashboard, our centralized hub that visualizes all incoming data, predictions, and system statuses. So how do these 5 features take shape in our project? They are consolidated into 3 main project components. The first component is our FloodWatch dashboard, a dynamic React-based interface that gives operators a live visual overview of regional water levels, active alerts, prediction outputs, and infrastructure states. The second component is our MATLAB Simulink environment, which models the control logic and simulates how pumps and sluice gates respond under different flood scenarios. The third component is our AI model prediction engine, which runs in the background to calculate the confidence score and probability of a flood occurring. To understand how these components communicate, let's walk through the system pipeline. The system operates as a continuous 7-step monitoring and response loop. Step 1 is the real-time environmental data acquisition. The system gathers live environmental metrics from the field using a tipping bucket rain sensor, soil moisture sensor, and radar water level sensor. Step 2 is the sensor fusion layer. Instead of processing each sensor reading separately, this layer synchronizes the asynchronous inputs and converts them into one clean unified dataset. From here, the fused data is passed into 2 decision engines. Step 3 is AI flood prediction, where the trained model generates a flood probability score. Step 4 is the rule-based flood type classification, which works in parallel to identify whether the likely flood condition is pluvial, fluvial, or combined flooding. Once a threat is confirmed, step 5 is the control system infrastructure response. This is where the system sends control commands to the simulated infrastructure, such as pump activation and sluice gate adjustment, to manage water flow before conditions worsen. Step 6 is dashboard monitoring, where operators are given full visibility of sensor readings, prediction outputs, alerts, infrastructure states, and manual override controls. Finally, step 7 is model retraining support. The system is designed to support future retraining using newly collected and validated environmental data. In the current prototype, retraining is treated as a back-end maintenance process rather than a live operator function. Next, I will pass the floor to Henry to discuss the testing and results obtained.
Thank you to Sharon for introducing the system features and the pipeline design. Moving on, my name is Henry and we will be putting the system to the test. Firstly, I will demonstrate how the system is used and the functionality of each component. Dashboard view where users can monitor various parameters, and it is split into three main sections: overall, area 1, and area 2. So it's controlled via this top navigation bar, and there's a toggle for dark and light mode. So looking first into the overall view, this section shows a summary for every region, which includes the river, rain, and soil moisture levels, plus a quick view on scores and AI verdicts. However, this does not show the full picture of the situation, hence the need for individual area cards. So for this project, we chose to display two different regions to show scalability in the project, allowing for multi-regional monitoring. The individual area shows the same 5 parameters as earlier, plus some additional ones, which includes the mitigation control here for our two infrastructures, the water pump and the sluice gate, plus the individual reading for every sensor before the sensor fusion, as well as the historical data, which is shown in a graph format for the three parameters. It can be collapsed to just view individual sensors. This provides a more complete understanding of each region on top of a human in the loop for mitigation control. So all the components here can be found in the MATLAB Simulink engine, except for the AI model prediction, which we will get into later. So moving into the Simulink, here we have two main components, which are the sensor fusion as well as the rule-based engine. For the sensor fusion, it takes in 9 total inputs, with 3 of them representing river, 3 representing rainfall, and 3 representing soil moisture. In actuality, rainfall and soil moisture are correlated, so the sliders can be combined. However, we chose to split it up for testing purposes. Out here is the fused value for each parameter. Down here we have the clock, which simulates each passing day as well as the seconds. So with each passing day, the rain level and soil moisture would reset. Here we have the normalized value for all 9 values that were pumped into it. And 3 of the values would then be passed into the rule-based flood controller. Additionally, we have other inputs here, which are the infra override, water pump, sluice gate, flood flag, and confidence score, which would act as interrupts for the rule-based engine, depending on how the monitoring team chooses to activate certain features. So it takes into account the flood flag as well as confidence score, which is predicted by the AI model. 1 being flood predicted, plus the corresponding confidence score, whereas 0 for flood flag means that no flood is detected. So when flood is detected, we would then return in the type of flood, the pump and gate percentage outputs, early mitigation if active, as well as the alerts and flood risk index, which is calculated from the rule-based engine. So we also decided on another thing, which is splitting the two regions into two different types of module. So in the first one, we simulate the sensors as closely to real life as possible via the sensor fusion module and the reset. However, for region 2, we chose to implement a testing sandbox where the sensor values are more direct. So we still have the same 3 individual sensors. However, we use a simple average, and this ensures that the values stay consistent as there is no clock. Hence, it is more stable for testing. So when the value is fixed to, say, 4 meters for river level, it would remain at 4 and will not fluctuate at all. So moving back to the dashboard, we have the AI flood prediction component, which uses the same 3 parameters that are seen here. And as shared earlier, the model was built using foreign dataset, meaning that the initial accuracy may not sync up with real-life situation in Cebu. However, in this system, we have employed a retraining feature. So here in the folder structure, we can see data. And here is our rolling dataset, meaning to say that it builds off of the original dataset with the new incoming ones. So we scroll the way down here. We can see area 1. So these are data that's logged for area 1, whereas region B would be for area 2. Here. So in the rolling data CSV file, new data is logged every X amount of seconds, which can be set. And when the set number of rows is acquired, say 1,000, the first 1,000 rows would be phased out while triggering the retraining phase. The new models would then be saved in an archive folder. would be in here. So it saves the various model and compares it, and it saves the best model for each region. So say model A would be for region 1, model B would be for region 2, and saves it in the current folder. So the current one would be the best performing model, which would be then loaded onto the system or the dashboard itself. This ensures uniqueness to the region, and with time the model would build itself to be specific to certain regions, for this case region A and region B. Moving on, we will be looking into the 5 different test scenarios to see how the system reacts to various situations. This includes pluvial flooding, fluvial flooding, compound flooding, manual infrastructure override, as well as rule-based and AI model conflicted output. First, we have the pluvial flooding test. For this test, the scenario trigger following our system design is rainfall being more than or equal to 30 millimeters per day, soil moisture greater to or equal than 70%, and river level being less than or equal to 2.9 meters. The following are the threshold values for different criteria such as normal, alert, and warning. For this test scenario, we used river level of 2 meters, rain of 91.3 millimeters, and soil moisture of 81.9%, fulfilling the trigger. These inputs return flood predictions as true, here, rule-based detection of 0.64, and flood type of pluvial. So here we can see that the mitigation control was automatically set to 70%, while the gate is set to still 0%. And these are the simulating output blocks, pluvial, flooding, 70% pump. Next, we will be covering the fluvial flooding test scenario. Similar to pluvial, this scenario also contains a trigger, which is river level greater than 2.9 meters, rainfall less than 30 millimeters per day. These are the threshold values that determine gate output percentages. And for this test, the river level was set to 4 meters, rain level of 34.8 meters, and soil moisture of 66.2%. This provided us with the following output, which is 0.47 FRI, flood predicted, and 30% gate opening with 0% water pump. It reflects in the simulating output blocks as well, and this is a warning which we will get into later. Fourth test scenario is the manual override infrastructure control. As you can see, the toggle for the override was enabled here in red, and this sends a payload of 1 to the simulating engine here. Once enabled, the pump and gate can be set to specific values from 0 to 100%, which reflects inside the simulating block here. So here we can see, here we set it to 70% and 100%. The action was locked, and it reflects here in the pump and gate settings. So the last test scenario is output conflict, specifically for disparities in rule-based FRI and AI prediction, with the trigger being FRI of less than 0.3 and flood predicted by the AI, sending flood flag equals to 1. These are the 3 different threshold values, with low treated as in error and no stern warning is provided. Medium, and a warning was shown, but there's no early mitigation active, while high confidence would activate the pump or gate depending on which value is set, plus a warning. So here we can see the output conflict. For example, FRI is 0.19, but flood is predicted. So the warning pops up, and the gate is automatically set to 30%, as the river level here, as seen, is rising. Due to the difficulty in testing this scenario, we have limited images and data available. However, we were able to achieve this by accident, and it proves that the system is working. It's just that it's difficult to test on because typically the prediction and the rule base would align. So what does the data show? Here we can see a summary table of all scenarios and their expected behavior, observed results and status. We can see that all the passes for the tests are achieved, meaning to say that we have achieved the design that we implemented. Moving on, we will look at the SWOT analysis, which summarizes the system's strengths, weakness, opportunities, and threats. For strengths, the main advantage is integration. The system combines sensor fusion, rule-based flood classification, AI prediction, dashboard monitoring, infrastructure control, and data logging into one working prototype. This allows users to monitor flood risk while also observing how the mitigation system responds. For weakness, the main limitation is the AI model and dataset. Since model uses foreign and synthetic data, it may not fully represent flood behavior in Cebu. It is also simulation-based, meaning that the results are tested in a controlled environment rather than with physical sensors. For opportunities, the system can improve further on local flood data once that becomes available. And with enough data logging, the model can be retrained to much better match Cebu's conditions. It can also be expanded into real-time IoT-based monitoring systems. For threats, the system depends on data quality and reliability. Noisy sensors, calibration issues, or connection failures may affect the output. The current dashboard also lacks authentication and encryption, which must be improved before real deployment. Next is the pest analysis, which looks at external factors that may affect the system. Politically, flood mitigation is connected to public safety and government planning, and a system like this could support disaster preparedness and smart city initiatives, but real deployment would still require approval from relevant authorities. Economically, floods can cause damage to homes, road businesses, and infrastructures in general, and with early prediction, it may reduce losses by supporting faster mitigation responses, although real sensors, maintenance, and integration would add costs. Socially, it can improve awareness by showing river level, rainfall, soil moisture, AI prediction, and infrastructure status in one dashboard. However, users still need to understand and trust the system before relying on it in real life situations. Technologically, the project uses Simulink, AI prediction, sensor fusion, backend APIs, and real-time dashboard, making it flexible, but it also depends on stable connectivity, accurate sensors, and reliable data processing. That will be all for my part. I will pass the floor to Mark to discuss on the takeaways.
Thank you, Henry, for the project demonstration. My name is Mark, and to wrap it up, I'll be walking you through the takeaway section of our presentation. This will cover 3 areas: how our project aligns with the UN Sustainable Development Goals, what could go wrong, and where we go from here. Our flood prediction system ties into 4 key SDGs, starting with SDG 3, good health and well-being. By providing early flood warnings, our system helps reduce exposure to flood water contamination, directly contributing to improved public health safety. Our runoff water management helps to reduce water pollution, and through real-time system regulation, we're also able to support broader water quality protection efforts, hence helping with SDG 6, clean water and sanitation. Through simulation-based and real-time monitoring, both of which strengthen urban flood resilience and improve disaster response capabilities, we also correlate our project with SDG 11, sustainable cities and communities. And finally, SDG 13, climate action. Our AI-driven prediction system builds resilience against extreme weather events while supporting adaptive data-driven flood mitigation strategies. After stress testing our system, the team has identified 4 key limitations to be aware of and potential failure points within our system. The first limitation lies within the AI model and dataset that was used. The historical training data we used was sourced from the Philippines and not Cebu, simply due to the lack of locally available data. We also supplemented it with synthetically generated data to help build and shape the prediction pipeline. However, this is not ideal for accurately mimicking real flood events specific to Cebu. What this means in practice is that early predictions may be less accurate until the system accumulates enough local data to retrain and calibrate itself to Cebu's specific environmental conditions. The second potential limitation is the system's dependency on sensor fusion and calibration. Our sensor boundary input values are currently configured based on the limits set by the Sarawak Maritime Station and the Express Terminal Station in Cebu. Any deployment to a different region would require these values to be reconfigured accordingly. On top of that, our current sensor fusion relies on relatively simple mathematical approaches, such as median and mean calculations, which may not be robust enough for all real-world conditions. Third is the simulation to real-world gap. Our simulation works with fairly optimal inputs, and while we introduced noisy data for added realism, we did not have access to physical sensors. In an actual deployment, raw sensor data would be far noisier and more unpredictable, meaning significantly more robust data filtering would need to be implemented. Lastly, there is dashboard security. Our current system has no encryption or authentication in place, leaving it vulnerable to man-in-the-middle attacks and fabricated or malicious data injection by anyone with knowledge of the system's inner workings. This is a serious cybersecurity concern that would need to be addressed before any real-world deployment. Looking ahead, there are 4 directions the team believes this could be taken further. For community integration, a public warning API that connects our front end to an automated SMS or push notification service could give residents direct, real-time flood alerts, significantly increasing the system's community value as an early warning tool. For system resilience, a fail-safe fallback mechanism could be built into Simulink so that pumps and gates can continue operating safely even if a physical sensor goes offline. For AI and local data optimization, integrating GIS elevation maps would allow street-level flood mapping, identifying which low-lying areas could submerge first. This could tie directly into early warning systems to give residents advance notice to evacuate. And lastly, for advanced automation, rather than the current binary open-close sluice gate control, future iterations could implement variable gate opening percentages based on a risk flood index, making the system's response more gradual and precise. And with that, I'll hand over to Sharon for the conclusion.
To wrap up, our project directly tackles the dangerous delays caused by today's manual and reactive flood management systems. We have replaced this with a proactive, AI-driven prediction model that continuously auto-retrains itself using live environmental data. By implementing a unified sensor fusion layer, our system bridges intelligent software with heavy physical infrastructure, allowing it to autonomously trigger sluice gates and water pumps before a flood even hits. Ultimately, this system goes beyond just smart technology. It advances global sustainability by protecting public health and water quality for SDGs 3 and 6, while significantly enhancing urban climate resilience for SDGs 11 and 13. Thank you all for your time.